Hello everyone, welcome back to my YouTube channel. In this particular video, we will be looking into a very interesting topic which is commonly called as Betweenness Centrality. So let's start with an overview of this particular topic. So what exactly is Betweenness Centrality? So it is nothing but a measure of node's importance based on the shortest path that passes through it. Now, in a network we have multiple nodes as well as multiple edges that connects the nodes. Out of those nodes, if you want to calculate the betweenness centrality of a particular node, then it can be calculated by just looking at the total number of shortest paths that are present between any two nodes. And the node whose betweenness centrality we want to calculate, if that particular node is present between this shortest path, then the presence of the node between the shortest path will account for the betweenness centrality. The node is present in more number of shortest path, then the betweenness centrality of that particular node will be more. I hope it is clear. If still it is not clear, then don't worry, we'll be looking into an example which will clear all your doubts. Now, this measure of betweenness centrality identifies the critical connectors in the network. Now, note one thing, that betweenness centrality is just one of the several measures of calculating the node's importance. Now, to calculate betweenness centrality of a node which is present inside a complex network can be computationally very much expensive, because here we have to look all the possible paths as well as all the possible iterations. So it takes a lot of time as well as lot of computational resources to calculate this. Now this measure of betweenness centrality is basically useful in social networks, transportation networks as well as in biological networks. By calculating the betweenness centrality, we can come to know which particular node is acting as communication medium between several nodes present in the network. Hence, this is a very important concept. Now, here I have given you a very simple overview example to know more about betweenness centrality. So the scenario is like this. Suppose you have a social network of 10 people. That means you have 10 nodes in a particular network. All these people or nodes are connected to each other in some fashion. Now, you are calculating the betweenness centrality of each and every node, and you found out that person A, that means node A in the network, has the highest betweenness centrality. Now what does that mean? This means that the person A or the node A is acting as a bridge or a communication medium between several nodes that are present inside the network, and this is a critical node which is actually concerned for transfer of information flow from one community of the network to the other community. Presence of the nodes which has the highest betweenness centrality in a network will increase the communication flow between several nodes in the network. If you remove this particular node with highest centrality from the network, the communication or the overall structure and functioning of the entire network will shatter, or the flow of information will get slower. So I hope by this small example, the concept of betweenness centrality is clear to you all. Now we'll look at the formula for finding the betweenness centrality of the nodes. So betweenness centrality, that is denoted by BC of any node. Let's say the node is Y. Y is here a vertex from the entire network, and it can be given as by this formula. That means BC of Y will be summation of, with a condition that the source and the destination node should not be same. Here in our case, source node is X and destination node is Z. We are actually checking whether the node Y is present between the source node X and destination node Z. We are calculating the betweenness centrality of the node Y. So it can be given as sigma xz of the node Y divided by sigma xz, where sigma xz of Y is nothing but the total number of shortest path from X node to the Z node which contains the node Y in between. So I hope this is clear. This is nothing but the shortest path that contains the node Y in between the node X and Z. And the next part is sigma xz, which is nothing but the total number of shortest path from X to Z, which may or may not contain the Y node in between. So I hope this is clear. Now using this particular formula, you can find out the betweenness centrality of any single node which comes in a particular path. Now this is for a single path. Similarly, every single node's betweenness centrality has to be calculated for every single combination of paths in a given network. So now we'll be looking into an example which is going to be following this particular formula and which will clear all your doubts. So here the question says that we need to calculate the betweenness centrality of all the nodes and we need to find out the node with highest betweenness centrality from this particular graph. And the graph contains total 6 nodes A, B, C, D, E, F. You can see that these nodes are connected with each other with some particular manner. And note one thing, that all the edges are bidirectional. That means A can go to B as well as B also can go to A. Now we'll have to calculate the betweenness centrality for every single node. So here let's consider the first node as A node. We have the formula for calculating the betweenness centrality. Based on this formula we'll be calculating it. Now we need to construct a table. The table might look big, but let me show you the correct way to read it. First we have to write the paths, all the possible paths without including the node for which we need to calculate the betweenness centrality. So here in this particular case, node A is the concerned node. So without the node A, whatever paths are possible, we have to write it. We'll have to start with B. So BC is one path, then go in alphabetical order. BD is another path, BE, then BF, then we can start with C. So all the possible paths from C are CD, CE, CF. Note one thing, that we cannot go back to CB because BC is already written. Okay, so you have to write it in one single direction because there is no direction in the graph. The edges are non-directional. Next we have to write from D, so DE and DF, and finally we are left with EF. So these are the all possible paths that are present inside this particular graph excluding node A. Now next column in the table is sigma xz of y. This is going to contain all the possible shortest path from node x to node z, which contains the node y in between. Similarly, the next column is sigma xz, which contains all the possible shortest path from node x to z, which may or may not contain the node y in between. And the last column contains the betweenness centrality formula, which is nothing but division of sigma xz of y divided by sigma xz. Now let's start to fill this table. So first path we have BC. You can see in the graph B is directly connected to C. So there is only this shortest path present that connects B and C. Apart from this path, there is no other shortest path. Hence, we have to write 1 in place of sigma xz. Now, can you just tell me whether A node, which is concerned node, is present inside this shortest path BC? It is not, right? So therefore we write 0. And once we calculate both these values, we have to divide this. So 0 divided by 1, it is 0. So hence the betweenness centrality of the path BC with respect to the node A is 0. Now the next path is BD. So you can see that from B to the node D, we can reach from two shortest paths. Either we can go from the path BAD or we can go from the path BED. Apart from these two paths, we do not have any other shortest path. So we can write in place of sigma xz 2 as the value. Now out of these two shortest path, one shortest path contains the node A. Hence we'll write 1 in place of sigma xz of y. Now we will have to divide these two values. 1 divided by 2 gives us 0.5. Therefore 0.5 is the betweenness centrality of the path BD with respect to the node A. Next path is BE. You can see that BE is directly connected with an edge. So there is only one single shortest path, and in this shortest path there is no role of the node A. Hence we'll write 0. 0 divided by 1 is 0. So the next path is BF. Again BF is directly connected to each other and there is no role of A. Hence we'll write 1 in place of sigma xz and 0 in place of sigma xz of y. The division of these two values gives us 0. Next path is CD. You can see that there is only one single shortest path to reach from C to D, and the path goes like this: CED. You can see that the other path CBED is not the shortest path, so we'll only consider the single path, that is CED. There is only one single shortest path, and this particular shortest path does not contain the node A, hence the betweenness centrality of this particular path will be 0. The next path is CE. Since it is directly connected, the betweenness centrality is 0. Again, the next path is CF. Again, it is directly connected, it will be 0. Next is DE. Again, DE is directly connected to each other, the centrality will be 0. Next is DF. Now you can see that there are total 3 possible paths from D to F. First is DABF, next is DEBF, and next is DECF. All these 3 are the shortest path, so you can write in place of sigma xz as 3. Out of these 3 paths, there is only one single path which contains the node A, that is DABF, and therefore we can write 1 in place of sigma xz of y. So 1 divided by 3 gives us 0.3333. The last path is EF. So you can see that for reaching from E to F, we have 2 shortest path. One is EBF and other one is ECF. So in place of sigma xz, we can write 2. Out of these 2 paths, we do not have any single path that contains the node E. So therefore we can write 0. Now after calculating the betweenness centralities of all the paths, we'll have to add all these centrality measures. After that we get 0.8333 as the answer. So you can say that the betweenness centrality of the node A is 0.83333. So this is how we calculate the betweenness centrality of each node. Similarly, now we'll have to calculate the betweenness centralities of every single node present inside the network. So the next node is node B. So now we'll have to consider node B to find out the betweenness centrality using this particular formula. Again, we'll have to construct the table. Now this time you'll have to change the paths because the node has got changed. Without node B, how many total paths you can write, you will have to write inside the table. Always try to write it in alphabetical order to avoid any mistakes. So you can see any of the path is not having any source or destination node as B. So these are all possible paths: AC, AD, AE, AF, CD, CE, CF, DE, DF and EF. These are all possible paths. Now we'll have to calculate for AC. So for reaching from A to C, we have only one single shortest path, which is ABC. Hence in place of sigma xz, we need to write 1. Now in this possible shortest path, we have the node B also. So therefore we'll write 1 in place of sigma xz of y. 1 divided by 1 gives us 1. So the betweenness centrality of the path AC with respect to the node B is 1. Next path is AD. You can see that AD is directly connected. Whichever nodes are directly connected, we'll have to write the betweenness centrality as 0. Next path is AE. You can see that there are 2 possible paths for reaching from A to E. One is ABE and second is ADE. Out of these 2 possible paths, we have only one single path which is containing the node B in it. So therefore 1 divided by 2 will give us 0.5. The next path is AF. ABF is only shortest path. In this shortest path, B node is also coming. Hence both sigma xz of y and sigma xz will have the value 1. 1 divided by 1 is 1. Next path is CD. You can see that for reaching from C to D, we have only one single shortest path, which is CED. In this shortest path, we do not have the node B. Hence, the centrality will be 0. The next path is CE. For reaching from C to E, we have a direct edge which is connecting. Hence, the centrality will be 0. Next is CF. Again, it is a direct edge that is connecting these 2 nodes. Hence, the centrality measure will be 0. Next path is DE. DE is again directly connected with each other. Hence, the centrality measure will be 0. Next is DF. Now you can see that for reaching from D to F, we have 3 possible paths. First is DABF, second is DEBF and third is DECF. Out of these 3 possible paths, we have two possible paths which contains the node B in it, which is DABF and DEBF. So therefore we can write 2 in place of sigma xz of y. 2 divided by 3 gives us 0.6667. The next path is EF. For reaching from E to F, we have two possible paths. One is EBF and second is ECF. Out of these two possible paths, we have one possible path which contain the node B in it. So, which is ECF. Hence, we'll write 1 in place of sigma xz of y. 1 divided by 2 gives us 0.5. Now we'll have to add all these betweenness centralities of all the path to get the betweenness centrality of the node B. After adding, we get the value as 3.667. So this is the centrality of the node B. I hope it is clear. Now similarly we'll have to find it for the node C. So now you can see that C is the concerned node and we'll have to construct all the paths without accounting the node C as a source node or destination node. So you can see that AB, AD, AE, AF, BD, BE, BF, DE, DF and EF are all possible paths for this particular situation. Let's start with the path AB. You can see that AB is directly connected with an edge, hence the centrality measure of AB will be 0. Similarly, AD is also directly connected, hence the centrality measure of AD will be 0. AE is having two possible paths, that is ADE and ABE. Out of these two possible paths, we have 0 possible paths that contains the node C into it. Hence we'll write 0 in place of sigma xz of y. 0 divided by 2 gives us 0. The next path is AF. There is only one possible path, ABF, to reach from A to F. And in this particular possible path, we do not have the node C between it. Hence, the centrality measure will be 0. Next, we have the path BD. So for reaching from B to D, we have two possible shortest paths. First path is BAD and second path is BED. Out of these two possible shortest paths, we do not have any path which contains the node C. Hence we'll write 0. 0 divided by 2 gives us 0. The next path is B to E. You can see that B is directly connected with E. Hence the centrality measure of BE will be 0. Next is BF. The BF nodes are directly connected with each other, hence 0 will be the centrality measure. Next is DE. Again DE is directly connected with each other, hence the centrality measure of DE will be 0. Next path is DF. For reaching from D to F, we have three possible shortest paths. First is DABF, second is DEBF and third is DECF. Out of these three possible paths, which are the shortest path, we have only one single path which is having the node C, which is DECF. Hence, in place of sigma xz of y, we'll write 1. 1 divided by 3 gives us 0.333. Next path is EF. So, for reaching from E to F, we have two possible paths. First is EBF and second is ECF. Out of these two possible shortest paths, we have only one single path, that is ECF, which contains the node C in it. 1 divided by 2 gives us 0.5. Now, after calculating the centrality measures of all these paths, we'll have to add it to get the centrality measure of the node C. So here 0.8333 is the betweenness centrality of the node C. So I hope now you have become a pro to calculate the betweenness centrality of any single node. Similarly, we'll have to calculate the betweenness centrality of the node D. Here, without the node D, you will have to calculate all the paths. You can see the first path AB is directly connected with each other, hence the betweenness centrality of AB will be 0. Next is AC. AC is having one single shortest path ABC which doesn't have the node D into it, hence the centrality measure will be 0. AE has two possible paths, first is ABE and second is ADC. Out of these two possible paths, we have only one path that contains the node D in it. That path is ADE. So you can see that the centrality measure will be 1 divided by 2, which is 0.5. Similarly, you can find it for AF. AF has only one single shortest path, ABF, which doesn't have the presence of node D in it. Hence, the centrality measure will be 0. Next path is BC. You can see that BC are directly connected with a single edge. So the centrality measure will be 0. Next path is BE. Again you can see that BE is directly connected with an edge, hence the centrality measure of BE will be 0. Next is BF, again they are directly connected, hence the centrality measure of BF with respect to the node D is 0. Next is CE. CE is again directly connected, hence the centrality measure will be 0. CF is again directly connected, the centrality measure of CF with respect to node D is 0. Next is EF. Now from E to F you have two possible shortest path, one is EBF and second is ECF. Out of these two possible shortest path, you don't have any single path which goes from the node D. Hence 0 divided by 2 will be 0. Now add all the centrality measures of every single path, you get 0.5 as the betweenness centrality of the node D. Now similarly you need to find out the betweenness centrality of the node E. Here you need to frame all the paths without considering the node E as source or destination node. So these are all the possible paths. Let's see the first path. The first path is AB. You can see that A and B are directly connected, so the centrality measure will be 0. AC has a path ABC which doesn't have the presence of the node E. Hence the centrality measure will be 0. AD path is directly connected with a single edge, hence again the centrality measure will be 0. Next is AF. AF is having the shortest path ABF which doesn't account for the node E inside it, hence again the centrality measure will be 0. Next is BC. BC are directly connected with each other, hence centrality measure will be 0. Next is BD. You have two possible paths for reaching from B to D. You have first path as BAD and second path as BED. So 2 will be sigma xz. And out of these two paths we have only one single path which is BED which contains the node E in it. Hence 1 divided by 2 will be 0.5. The next path BF is directly connected with an edge, hence the centrality measure will be 0. Next is CD. You can see that CD is connected with a single path which is shortest path which is CED, hence sigma xz will be 1. Now this particular shortest path also contains the node E in it, hence sigma xz of y will be 1. 1 divided by 1 is 1, hence the centrality measure of CD will be 1. Next is CF. CF is directly connected with an edge, hence the centrality measure will be 0. Next is BF. You can see that for reaching from D to F we have three possible shortest path. First is DABF, second is DEBF and third is DECF. So sigma xz will be 3. Out of this three shortest path we have two possible shortest path which contains the node E, DEBF and DECF. So 2 will come in place of sigma xz of y. So 2 divided by 3 will give us 0.6667. So after adding all the centrality measures we get 2.1667 as the centrality measure of node E. Similarly we'll have to calculate the centrality measure for the last node which is the node F. Here you will have to calculate all the paths which doesn't contains the node F as source or destination node. So these are all the possible paths. Let's start with the first path, that is AB. AB is directly connected with each other, so 0 will be the centrality measure. Next path is AC. You can see that for reaching from A to C we have only one single path, that is ABC, and in this path we do not have the node F as the center node. So 0 will be the centrality measure. The next path is AD. AD is directly connected with an common edge, hence 0 will be the centrality measure. Next is AE. AE has two possible shortest paths, ABE and ADF. Out of these two possible shortest paths we have 0 paths that contains the node F in it, hence 0 will be the centrality measure of the path AE. Next path is BC. BC is directly connected with each other, hence 0 will be the centrality measure of it. Next is BD. Now you can see that for reaching from B to D we have two paths, BAD and BED. Out of these two paths we do not have any single path which contains the node F, so 0 is the centrality measure. Next is BE. Again BE is directly connected, hence centrality measure is 0. Next is CD. You can see that C is connected to D with a single path, that is shortest path which is CED, which does not contains the node F into it. So 0 divided by 1 will give us 0. Next is CE. CE is directly connected with each other, hence the centrality measure of CE will be 0. Next is DE. DE is again directly connected with a common edge, so 0 will be the centrality measure. So after adding the centrality measures of all the paths for the node F we get 0 as the betweenness centrality of the node F. Now once we calculate the betweenness centralities of all the nodes that are present inside the network, we'll have to write it in a single table. So you can see that A, B, C, D, E, F has these as the betweenness centralities. Now once you write it in a table, next you need to find out the maximum betweenness centrality, and here you can see that the node B has the highest betweenness centrality. So therefore you can conclude that node B is the one which acts as a connector or the communication medium between all the other nodes that are present inside this particular network. If we try to remove this node B, which has the highest centrality measure, then you can see the graph will look something like this. Now, if we try to reach from A to F, we'll have to traverse through all the nodes A, D, E, C, F. So, doesn't that make it slower for transferring information from one node to other? Similarly, if you want to traverse from C to A, we'll have to go to the node E first and then the node D. So this makes it slower for transferring the flow of information, and it is the reason why the delay occurs in a social network or any other network. And now if we put this B node back to the graph, you can see that for traversing from A to F, now you just have to traverse from the node B. That is, the path shrinks to only ABF. You just have to traverse through a single node. Similarly, if you want to move from C to A, you will have to traverse through only a single node, that is B. So this increases the rate of information flow between the nodes, as well as in complex or wider networks, it acts as a connector between different communities as well as different clusters of this network. So hence, I hope that the concept of betweenness centrality, the way to calculate it and the use of it is clear to you all. Now I request you all to please go and subscribe to my channel if you like my video. Please hit the like button as well as share this video with your friends so that they can get the benefit of this. Follow me on Instagram, and thanks for watching.